we have a flight control issue, and we've got at least 3 people injured.
After the JetBlue incident in October 2025, public attention briefly turned to the effect of high-energy radiation on aircraft systems. Engine control engineers, however, have been designing around this reality since the late 1990s, and while their solutions cannot be applied directly to flight controls, they reveal perfectly how engineering assumptions shape safety when internal data can no longer be trusted. To understand where those assumptions came from, we have to look at the environment where digital engines were born. The timing here is actually important. In the early 1980s, most aircraft systems were still controlled by cables, pulleys, and hydraulics. Flight computers existed, but they moved the same cables the pilot did. If the computer failed, the pilot could just take over. Engines were the first system to break that rule. They went fully digital first, with no mechanical backup and no manual override. The computer had complete control over fuel flow, compressor vanes, and turbine temperatures. This was called FADEC, which stands for Full Authority Digital Engine Control, and that full authority part is the key. The computer controlled everything, or the engine didn't run at all. In the mid-80s, this was a terrifying proposition. Personal computers of that era were unreliable toys that crashed constantly. Removing the mechanical safety net felt like madness to traditionalists, but airlines were desperate for fuel efficiency, and digital control was the only way to get it. The industry was effectively betting the safety of the aircraft on the reliability of a microprocessor. Airlines needed the efficiency gains that digital control promised. Boeing was pushing for it on new aircraft, and the engine manufacturers had to figure out how to make it work safely enough that nobody would die if something went wrong. We spoke with an engineer who watched this entire transformation happen firsthand. He started working on engine controls in 1985 and continued in the field through 2015, which means he spent 30 years watching these systems evolve from mechanical controls to the sophisticated digital systems we have today. He watched FADEC mature from a risky innovation into the reliability backbone that allowed ETOPS twins to conquer the oceans. But in the mid-90s, the data took a strange turn. Engineers began seeing anomalies that technically shouldn't have existed, logic errors that defied the code. These weren't mechanical failures. They were the first operational signs of cosmic radiation striking commercial hardware. Our engineer started in 1985, and he already had a path for him set up.
When I started out, my boss wanted me to become a hydromechanical specialist. I got extensive training in the details and subtleties of those controls.
These weren't simple systems by any measure. They were mechanical computers, essentially, incredibly sophisticated pieces of engineering. The basic operation was straightforward enough. The pilot moves the throttle, which moves a cable, which adjusts a mechanical fuel control unit. That unit meters the right amount of fuel based on altitude, temperature, and engine speed, all done mechanically through physical components you could actually see and touch. The defining characteristic of these systems, though, was how they failed.
Hydromechanical systems tend to give you warnings when something is wearing out. You'd see leakage, loss of tension, slow drift in behavior. Electronics don't generally do that. They either work or they don't.
That gradual failure mode was absolutely critical for maintenance operations. A seal would start leaking, a linkage would show wear, performance would drift slightly over time. Maintenance crews had clear indicators that something needed attention before it became a real problem. You got advance warning with mechanical systems, which gave you time to plan maintenance and avoid surprises. By the time our engineer was getting trained on all this sophisticated mechanical hardware, though, the industry was already moving away from it. The 1970s oil crisis had changed everything about airline economics. Fuel costs went through the roof, and airlines were desperate for any efficiency gain they could get. That put enormous pressure on engine manufacturers to deliver tighter, more precise control over every aspect of engine operation. digital control offered a solution to that problem. A computer could adjust fuel flow, variable stator vanes, and bleed valves in real time with far greater precision than any mechanical system could achieve. It could optimize performance continuously based on actual conditions rather than relying on predetermined mechanical settings. The efficiency gains were measured in percentage points of fuel consumption, which for airlines operating hundreds of flights a day translated to millions of dollars per year in savings. Our engineer saw where this was heading almost immediately, even though he'd just been trained as a hydromechanical specialist.
Within a few years, it became quite obvious that FADEC was taking over, and doing strictly hydro stuff was a dead end. So I soon expanded into FADEC.
In 1984, that digital future arrived in commercial aviation. In November of that year, Delta Airlines took delivery of the first Boeing 757 powered by the Pratt & Whitney PW2037, which was the first commercial aircraft engine with full authority digital control to enter revenue service. That engine used what's called dual-channel FADEC, which means two independent computers, with each one capable of running the engine completely by itself. If one channel detected a problem, the other would take over seamlessly without any interruption in engine operation. There was no mechanical backup and no manual override. The computer controlled everything, or the engine didn't run at all. From the pilot's perspective, FADEC simplified operations considerably. You moved the throttle lever and the system handled the rest, allowing you to slam the throttles without worrying about compressor stalls or overtemps. The result was better fuel efficiency, better performance, and significantly less cockpit workload. For the engineers, this was equal parts terrifying and exciting. The industry was making a fundamental bet that software could be trusted with complete engine authority, a massive departure from aviation history. Then, Boeing forced the issue. During the design of the 747-400, they made a radical decision that would make this digital transition mandatory. At the time, the GE CF6 was in widespread use on the 747-300. It was a proven, reliable engine with thousands of hours of experience. But to get onto the -400, GE had to create a new variant. They updated the model number with a specific suffix, F, and that F stood for FADEC.
Boeing told GE they wouldn't put throttle cables in the 747-400, so if they wanted on, they needed to create a FADEC version.
The reason for that ultimatum was strategic. Boeing was redesigning the 747 to be flown by 2 pilots instead of 3, effectively deleting the flight engineer's station. Without a third person to constantly fine-tune 4 mechanical engines, they needed engines smart enough to manage themselves. That decision essentially made FADEC mandatory across the entire industry. If Boeing wasn't going to accommodate mechanical controls on their new flagship, every engine manufacturer had to go digital or risk being shut out of major contracts. By the late 1980s, FADEC had become the industry standard across all major manufacturers. Pratt & Whitney had their PW2000 and PW4000 families with digital control. GE was rolling out FADEC versions of the CF6. Rolls-Royce was developing digital controls for the RB211. The transformation from mechanical to digital was essentially complete. Something else was happening at exactly the same time, though, and engineers were paying close attention to this development as well.
ETOPS was becoming a big thing about the same time, and the full FADEC PW4000 and CF680C2 engines were being certified for use on the 767.
Airlines wanted to fly twin-engine aircraft across oceans on routes that had always required 3 or 4 engines for redundancy. For that to work, the engines had to be incredibly reliable, more reliable than anyone had proven before in commercial aviation. On February 1st, 1985, Transworld Airlines flew the first commercial ETOPS 120 flight, a twin-engine Boeing 767 from Boston to Paris. This was genuinely revolutionary because a twin was now allowed to fly up to 120 minutes from the nearest alternate airport, whereas previously twins had been restricted to just 60 minutes from a suitable landing site. This essentially prevented them from carrying passengers over oceans. The economics were absolutely compelling. That 767 burned 7,000 pounds less fuel per hour than the L1011 TriStar it replaced on the same route. TWA was so convinced of the savings that they spent $2.6 million per aircraft retrofitting their entire 767 fleet to meet ETOPS standards, which was a massive investment, but one that would pay for itself through fuel savings. The FAA wasn't just going to let this happen without extensive proof, though. They required comprehensive data on system reliability. Boeing had to provide trend monitoring systems to track in-flight reliability of every critical system. Engineers worked on proving FADEC reliability during this era, and the initial approach was deliberately conservative.
As a starting point, we looked at the historical rates of hydromechanical control-caused shutdowns and loss of thrust control, and targeted reliabilities that would mirror those rates for FADEC with necessary shutdown and LOTC rates to meet the ETOPS requirements.
They were being cautious with good reason. The plan was to match the reliability of the proven mechanical systems that had decades of operational history behind them. If FADEC could demonstrate it was at least as reliable as hydromechanical controls, they'd meet minimal ETOPS requirements and everyone could move forward with confidence. Something unexpected happened, though. As the data accumulated over thousands and then hundreds of thousands of flight hours, it became clear that FADEC was significantly more reliable than the mechanical systems it replaced. Not just as good as mechanical systems, actually better by a substantial margin. This wasn't what anyone had predicted when they started the certification process. That higher than expected reliability opened new doors. In 1988, the FAA extended ETOPS to 180 minutes based on the proven reliability data. By 1989, American Airlines was flying the Dallas to Honolulu route with ETOPS 180 certified 767s, crossing the Pacific with a twin-engine aircraft. By 1993, all variants of the 767 family had achieved ETOPS 180 certification. The market shifted dramatically over just a few years. By 1991, more passengers were crossing the Atlantic on 767s than on any other aircraft type, which was a complete reversal of historical patterns. By 2000, over 50% of all transatlantic crossings were being made by twins. The reliability that FADEC enabled had made possible something nobody thought achievable just a decade earlier. Today, modern twins routinely operate with ETOPS 330 certifications, which means they can fly 330 minutes, 5.5 hours, from the nearest alternate airport. Engine reliability has become so good that it's almost never the limiting factor for route planning anymore. FADEC made that entire transformation possible. As FADEC became ubiquitous across the industry and the technology continued to mature through the 1990s, though something started changing that engineers began to notice. The chips themselves were evolving in ways that would create an entirely new set of problems. Through the 1990s and into the 2000s, integrated circuits were getting smaller and more powerful with each generation. Moore's law was in full effect across the industry, and each new generation of chips packed more transistors into less physical space, required lower operating voltages, and stored less electrical charge per individual bit of data. Cosmic rays come from distant stars, while solar particle events come from our own sun. When these high-energy particles hit the atmosphere, they create cascades of secondary particles. The most common of these at cruise altitude are neutrons. In fact, at 35,000 feet, roughly 55% of the ambient radiation is just neutron bombardment. When one of these high-energy particles hits a semiconductor chip, it can deposit enough energy in a sensitive region to flip a bit from 0 to 1 or from 1 to 0. This is called a single-event upset. With the older, larger chips that used higher operating voltages, the electrical charges holding each bit in place were strong enough that even if a particle hit the chip, it usually didn't have enough energy to actually change the bit state. As chips got smaller and operating voltages dropped with each generation, that natural immunity evaporated. By the late 1990s, engineers were seeing the evidence in the field.
As newer generations of integrated circuits became smaller and more powerful, single event upset became a concern. A high-energy particle hitting a CPU or memory chip and causing a bit to change state.
These weren't just theoretical problems that might happen someday. They were showing up as actual events in operational aircraft.
With older circuitry, the electrical charges were strong enough that even if a particle hit, it usually didn't have enough energy to change the bit state. With newer stuff, processors were using a lot less power, but that occasionally became a real issue and could lead to loss of thrust control events.
This would be a serious incident. The engine is running and producing power, but something in the control system isn't behaving the way it should. These events took a long time to understand fully, because they were random and extremely difficult to reproduce in testing. You couldn't predict when or where a cosmic ray would hit a specific chip in a specific aircraft. Eventually, patterns started emerging from the accumulated data across thousands of flights. These events happened more frequently at higher altitudes, where there's less atmospheric shielding. They happened more frequently at high latitudes, where Earth's magnetic field provides less protection against charged particles. They happened more frequently during periods of high solar activity, when the sun was throwing out more radiation. All the evidence was pointing clearly toward atmospheric radiation as the root cause. By the late 1990s and early 2000s, the industry understood they had a genuine problem on their hands. The same technology advancement that was making FADEC more capable and more efficient was simultaneously making it more vulnerable to space radiation. This vulnerability wasn't going to get better on its own either. As chips continued to shrink with each new generation, the susceptibility to single event upsets would only increase. The question facing engineers was, how do you protect a system from random particle strikes that you fundamentally can't predict and can't effectively shield against? Shielding doesn't work well against high-energy neutrons. They just pass right through most materials. Teams of engineers started working on finding a way out of this problem. FADEC engineers developed a solution that was very simple. Don't try to stop the physics. They knew they couldn't shield against high-energy neutrons. So instead of trying to prevent the data corruption, they designed the system to assume it will happen and to kill it immediately. Our engineer explains exactly how this mechanism works inside the box.
The newer FADECs run constant checksum type checks, looking for single event upset caused discrepancies. If one is detected, the channel automatically resets.
It can be done because the jet engine, even in mid-flight, is a slow beast. If a computer drops out for a few milliseconds to reset, the heavy turbine doesn't even notice. It doesn't affect the engine at all. Flight controls, on the other hand, don't have that luxury. Computers for ailerons and elevators operate in high-speed closed loops, and you cannot pause them to reset. A 50-millisecond gap at cruise speed could cause a dangerous transient jerk. That is why flight controls rely on filtering, asking, does this data make sense? Rather than resetting. And that is what failed on JetBlue 1230. The radiation hit, and the software, version L104, had filters that were too permissible. They accepted the corrupted data as real, and the plane pitched down. For engines, however, the detect and reset strategy has been a masterstroke. The system is so robust that it has actually changed the rules of how airlines operate.
The reliability of the FADEC electronics is so good that they've implemented time-limited dispatch, which allows extended dispatch with certain loss of redundancy faults up to and including losing a complete FADEC channel.
Think about that. The system is designed to be so resilient that you can fly with half of it broken, and the safety record backs that confidence up.
To date, no major commercial incidents or accidents have been traced to a FADEC engine control system issue since FADEC became widespread over 35 years ago.
Every commercial flight at cruise altitude is being bombarded by cosmic radiation right now, at this very moment. This isn't a rare occurrence or an unusual situation. It's constant and unavoidable. High-energy particles from space are interacting with aircraft electronics on every flight, every single day, all around the world. Engine engineers figured out how to handle that threat back in the 1990s and early 2000s when they first started seeing single-event upsets affecting their systems as computer chips became smaller and used lower voltages. They built FADEC architectures on the fundamental assumption that data corruption will eventually happen somewhere in the system, and they designed their response strategy accordingly. Aggressive checksumming to detect corruption immediately, automatic resets to clear the affected channel, multiple independent channels to maintain operation during resets. The architecture accepts that the threat exists and deals with it proactively rather than trying to prevent the impossible. Safety in aviation has never been about preventing every single possible failure from ever occurring. That's an impossible standard that no system could ever meet. Instead, it's about understanding thoroughly how systems can fail and designing them to handle those failures gracefully when they do inevitably happen. That's how we got to where we are today, by paying very close attention to the edge cases, the rare events that reveal assumptions we didn't even know we were making about how our systems would behave. The lesson that comes from the FADEC story is actually pretty clear. When you understand a threat thoroughly and in detail, when you design specifically for the actual conditions your system will face in operation, you can build something remarkably reliable. Reliable enough to fly twins across open ocean for hours at a time. Reliable enough that engines are rarely the limiting factor for anything anymore. Next time you're at 35,000 feet, look out at the wing. Those engines are detecting and correcting cosmic radiation hits on almost every flight, one of aviation's great unsung engineering achievements. Subscribe for more technical breakdowns.